Welcome to the Tucson Amateur Astronomy Association monthly meeting. We're so glad to have everyone here tonight. We have our regular members and we have people on Facebook as well. So we're delighted to see both groups attending. I'm May Smith. I'm the TAAA president. And helping me tonight is going to be Terry Lappin, who is going to be operating technology, and Jim Knoll, who's going to be interfacing with the Facebook people and also assisting some with the technology as well. I wanted to also welcome our Facebook people and let you know that you're very welcome to go to our webpage at TucsonAstronomy.org, and you're very welcome to, join as a member if you'd wish, and you can do that on our website. But we're certainly glad for you to attend any of our events, whether you're a member or not. And we're certainly glad to share anything on our website with you, and hope that you will receive some additional astronomy education from looking at that. So I would like to introduce our speaker for tonight, who is Joana Voigt. And Joana has attended school in Germany for several years and got a bachelor's degree and a master's degree in Germany. And then she now has been at the U of A for a while and obtained her master's in planetary sciences at the U of A. And she's working on her PhD now. So she's going to give us a presentation that is in her area of expertise as a planetary geologist. Joanna's presentation is going to be in two parts. One is going to be Earth and Mars, and then the second part will be Europa. So what we will do for questions is we will ask you to enter your questions in the chat for us. And when she gets to the end of her section on Europa and Mars, we will address all the discussion questions that come up. If you have a question that involves just understanding something she said or understanding a slide, we will interrupt her for those, but the longer questions will hold to the end. So we'll do the first part of her presentation, and then after that, she will give a second part of her presentation on Europa, and we will address questions the same way for that. And we will have some other sections to our meeting tonight when her presentation is completed. Then we will move to David Rossiter, and our Facebook will be blanked out probably for about 10 minutes then, when we have our voting on the bylaws changes that are being proposed. Then we'll come back on Facebook and we'll have Dr. Mary Turner with a second presentation tonight. So our Facebook people will be able to get two presentations tonight if they wish, and certainly our members will. So Joanna, are you ready to start your screen sharing at this point?
Yes.
Super.
So, okay. So can you hear me okay and see my presentation?
Yes.
Okay, perfect.
Looks
good. So thank you, first of all, for inviting me. I'm super excited to talk to you all, and yeah, I'm happy to talk a little bit about my research and also a side project that I recently did on Europa. So as May already said, the presentation will be split into two parts. The first is about analog studies of Martian volcanism, which is the focus of my PhD. And then the second one is generally, a little bit about cryovolcanic eruptions, and then also a work we just published in GLL last November. So May already introduced me, but I did wanted to add a few things. So as May said, I'm currently a PhD candidate at the Lunar and Planetary Laboratory here at the University of Arizona. And I'm originally from Germany, in Berlin, where I did my bachelor's and master in geological science. During my master's, I already was in Tucson for a year, for an exchange year, working with Christopher Hamilton. That's my advisor. You can see him on the right-hand side of the picture, even though from the back. And I really enjoyed working here at LPL, and I also love Tucson, and that's why I came back to do my PhD in Tucson. So I'm interested in eruption products on Earth, Mars, a little bit on the Moon, and icy satellites. And volcanic processes in general are expressions of the interior dynamics within a planetary body. And those studying volcanic surfaces allow us to get an insight into the volcanic, but also magmatic evolution of a planet or planetary body. And I'm especially interested in establishing fundamental links between the surface feature that we can see and then connect them to the interior dynamics. And for my PhD thesis, I focus on terrestrial analogs to Martian volcanism, including the Holarhöhen eruption site in the Icelandic highlands. That's also where I'm in the picture on the right and in the central part of the picture, and also in Elysium Planitia on Mars. So Mars' surface is dominated by volcanic processes. And what I show here is a digital elevation model from MOLA, which is a laser altimeter that is in orbit around Mars. And the high standing topography is here shown with warmer colors, and the low standing topography is shown with cooler colors. And I encircled the two largest volcanic provinces on Mars, Tharsis, which is shown here, and then with Olympus Mons, Asia Mons, Alba Mons, and a few other shield volcanoes, and then also Elysium with Elysium Mons. Just to the southeast of Elysium Mons is Elysium Planitia, which is a low-lying plane-forming unit that I marked here with the white border, and we are going to zoom into that box. So Elysium Planitia is particularly interesting because it experienced a turbulent but also very young history. It has the largest outflow channel that was fluvial carved on Mars, which is located here with my mouse cursor. I hope you can see that. It's called Mare Vallis. So this valley system was carved by fluvial activity only within the last 100 million years. And then it was filled by even younger lava flows. And these lava flows have a very high volume, and they are very young in respect to the Mars history of only about tens of million years. In Elysium Planitia, we also have Athabasca Vallis, which is the home of the youngest volcanic material on Mars, with only a few million years. So studying the recent history of Elysium Planitia will therefore provide us an insight into the hydrological, volcanic, but also magmatic evolution of the planet. And it is also very timely because NASA's InSight mission just landed in Elysium Planitia. It's a little bit outside the map, just to the west here. And so it's super excited to work in this area. In 2018, a study by Christopher and me revealed that the flat lava flows that are infilling Mare Vallis, so that are located here, contains several different lava morphologies, so the textures of the lava is very distinct. And that motivated me to try to understand what the controlling mechanisms are to form these different lava flow morphologies. Just to give you a short overview and an idea how the surface looks like on Mars. So on the left-hand side, we can see a highly disrupted lava crust that we sometimes call TAAA lava type or gravelly. On the right-hand side, you can see in contrast more continuous, more coherent crust. It experienced a lot of inflation, and we can see that because the surface is very characteristic of that. We have plateaus and small, they're actually not so small, they just look small in the image, and depressions. And they are associated with inflation, so of the lava crust. And these two types are the spatially most dominant lava types in Elysium planets.
Joanna, we did have one question about the slide. It was, how are such young surfaces dated as the Cerberus plains?
Okay, so was that the slide?
I think it was
probably.
I think it was the slide that you had up last, but I'm not totally sure. Alex, do you want to let us know which slide?
The one that's up right now is the one where she
Okay.
where you spoke about the different dates of the different units.
Okay. And what's your question?
Those are very young geologic features, and I just wondered what the method of dating something so young was. Whether it was return samples or cratering or what.
Yeah, so unfortunately we don't have samples. So the dating we use is crater size frequency distribution. So we analyze how many craters and how large the craters are in a specific area. So how much bombardment we had, and this can be related to the age. And that's the method we used to date the surfaces in Elysium planets.
Thank you.
Okay, so to give you an example of how lava types look like on Earth, we can see on the left-hand side a very brecciated lava, and on the right-hand side we call pahoehoe. It's composed of a smooth and coherent crust that builds up a thermally insulating crust. And the cool thing about these different lava morphologies is you can actually link them to different emplacement mechanisms. And this is very important because on Mars, we cannot just go and watch the eruption happen because first of all, the eruption already happened. And then it's hard to go to Mars. So it's very cool that the morphology can tell you something about the emplacement mechanism. For example, the TAAA lava is mostly emplaced in open channel system, and it's also thermally rather insufficient, so it loses a lot of heat. The viscosity regime is rather high, and it also gets in place when you have a high effusion rate. In contrast, the pahoehoe, it gets in place when you have low effusion rates. You build up an thermally insulating crust, and it's also emplaced in rather low viscosity regimes. So we know that the morphologies can be affected by different parameters, for example, the viscosity. And the viscosity can be controlled by the composition of the lava, the temperature, crystallinity, and so on. We also know that the morphology can be affected by the shear strain rate or the shear stress, and that can be affected by the effusion rate, the flow velocity, and the duration, but also the underlying topography. So to understand the controlling mechanisms, the first step would be to very well describe the lava morphologies we have on Earth, and then analyze the characteristics that are associated with them. The cool thing is that we had a recent eruption in Iceland, which is called the Holaherni eruption, and that is a perfect study site because, first of all, it was the biggest eruption we had in Iceland since 230 years. So it was very well monitored. We got a lot of information we normally don't have for these large lava flow fields. And the morphology is very fresh. On Earth, normally we have the problem that we have a high rate of erosion. So this is not the case at the Holaherni lava flow. Another good thing is it wasn't placed on a glacial outwash plain, which means the area is very flat lying, and we don't have a huge influence of pre-existing topography, which is a parameter that can control lava morphology. So we can exclude that. And another good argument why this is a good study site is the chemistry remained constant over the whole eruption, which is great because then we can also exclude that from parameters that affected the morphology. Just to give you an overview, so we are located in the highlands of Iceland, just north of the Vatnajökull ice cap. So here we have an outlet glacial, and the gray areas are the floodplains from the glacial, and this is the Holaherni lava flow field in dark blue, dark gray. Okay, so now we are looking at in flyover during the eruption, and I do want to bring your attention that even here when the lava was still hot and molten, we can see differences in albedo and also morphology. The texture sometimes is different. We can see breakouts. So here we still have molten incandescent lava that is in placing. On the back, you can see a lava pond where you start to crust over the incandescence of the molten lava. And now we are going to turn towards the active lava channel over here. So you can see that the lava was still flowing. I should say that the lava started in August 2014 and ended in end February 2015. So it was active for 9 months. You can still see that the lava is transporting with a kind of high velocity. So the lava is flowing through the channel, and now we can see the bend, which is called Bauger, and that was the main fetter that then transported the lava to up to 17 kilometers to the end. We can see spillovers of lava. And all right, so I don't want to go into a lot of detail here, even though I love to talk about lava morphologies. But I do want to bring your attention to two things. First of all, the lava occupied a very large area of 84 square kilometers. And the second thing is that what we can see here is a map of the different lava characteristics. And we divided them into a few units, but two of them dominate. The brownish unit, which is rubbly lava, and then the reddish unit, which is spiny lava. So these two lava types or lava morphologies dominated the whole Holaherni lava flow types. And they have very similar characteristics compared to the lava flow surfaces in Elysium Planitia. So on the left, we can see images in Elysium Planitia. So on the left, we have Mars, and on the right, we have Holaherni. Both surfaces have a disrupted crust. They have boulders in both images and also lineations. So the characteristic is very similar. Also, the second most common, which is the spiny lava flow type, often breaks out from the rubbly lava type, which is here shown in the central part. And this relationship we can also see on Mars. So not only that the characteristics of the morphology itself are similar, but also the relationship within or in between the different types are very similar. So what have we learned from Holohan? Well, first of all, I hope I convinced you that Holohan has very similar characteristics like we see in Elysium Planitia on Mars. Second of all, preliminary results showed that the lava morphology is indeed controlled by the effusion rate at Holohan. And if this holds, that would be a great result, because if we can actually say something about the emplacement evolution on Mars based on the morphology, that would be great, because it would even give us more important parameters to model the thermal evolution on Mars. And with this, I think I would stop here and would like to open the stage for questions.
Okay, I don't have any questions from our members at this point. I will move to Facebook. Facebook doesn't have any questions at this point. Does anybody have a question on Earth and Mars that has not been asked yet? If you do, please enter it in the chat.
Yeah, I have a question. What is the core of Mars? Is that known? Is it dead, or could it still be warm?
That's a very good question. And I wish we would have a good answer to that. So it should be cold by now. So Mars is much smaller than Earth is. However, there was a recent publication that was also just published by the end of 2020, and they suggested that they see pyroclastic deposits close to Cerberus fossae, which is a fissure also in Elysium Planitia. That's why Elysium Planitia is so great, because it's like the youngest feature that we see on Mars related to volcanic eruptions. So and I think they dated that being younger than 1 million years. So if that would be the case, they might be still magmatic activity, so heat on Mars. But I hope that InSight will give us more answers to that.
Okay. We have a question from Don, which is effusion rate controlled by viscosity?
Yes, so that's a good question. Let me go back. Okay. So the fusion rate itself, it's how much magma or lava is going to put out for a specific amount of time. So for example, if you have a very high viscous lava, then normally the effusion rate would be expected to be lower than if you have almost fluid-like moving lava. So it is related. I hope that answers the question.
Great. Thank you. Alex had a question that on the left image that you had, I think that you had up previously. I think it was like maybe your final slide, I'm not sure. What is the echo feature around the edge of the rough terrain?
Oh, okay. Is it, I guess the question is the white line.
No, on your last slide, the one that had there, and on the left-hand side, following the rough terrain, there's a ridge of some kind. No, other slide.
Other side.
There.
Oh, the other side? Okay.
No, yeah, there you go. That slide there, the one that says 1 kilometer on it.
Okay.
Okay. So it's just above you. There's the rough terrain there. Then just above it, there's a.
Oh yeah. That's a perfect question. So thank you for asking that. So that is actually the boundary between the different types of lava. So we have the very rough lava that is highly brecciated, and then we have the lava that is very similar to the one we see here that we call spiny lava. It could also be a pahoehoe lava. It is characterized by a continuous smooth surface. And so the idea is that the lava has the same age, even though it looks very different. And the idea here is that these smoother lava was a breakout from the rougher lava. But the unit itself, it could have been in place within a few minutes.
Okay. Let's see, my chat just moved, so I've got to read. Oh, Trey. David had a question about in what type of lava would one find lava tubes on Mars?
Oh yeah, okay. So that's a good question, thank you. Yes, so most of the time, let me see if I have, most of the time, if you want to get a lava tube, you need to build a crust, and a pahoehoe lava, so the smooth lava, does that a lot. So they build an isolating crust, and then they have tubes, like feeding system, lava pathway, and if they drain, we call them lava tubes. So the smoother is more likely to have lava tubes. Even though I would not completely say that we will never find lava tubes in rougher lava types. But I would look for the smoother ones first.
Bernie has a question of, does the lower atmospheric pressure on Mars have an effect at all on the lava texturing?
Good question. Okay. So it does have an effect how the lava gets transported, and for example, how the lava is cooling. So I'm not completely sure if we know the answer by now, but I would not think that the lava morphology would look completely different. Even though if we have, for example, precipitation like snow that we had in Hawaiian, we still see very similar characteristics compared to lava flows that were emplaced without precipitations. So the pressure should not, yeah. Okay.
John from Facebook asked, is all of Mars water locked up at the polar caps or frozen into surface itself?
Yeah, I really wish we would have the answers to that. So I think it is stored in the cryosphere, so of course at the polar caps, but also hopefully in the very porous rocks of Mars. But we haven't seen any strong evidence. For example, with radar instruments, we have 2 radar instruments on Mars. They should be able to see subsurface water, and we have not found it yet. Okay, should we move towards the outer solar system, or do we have more questions?
I think so. No, that seems to be the end of the questions. We do have some thank yous, but it looks like we're ready to move on.
Okay, perfect. Okay, so I will just give a very brief overview on cryovolcanism and then talk about a paper that we have published in November. last year. So there are a lot of planetary bodies where cryovolcanism could have happened, or maybe still happens. But the two prime candidates are Europa, which is the icy satellite of Jupiter, and then Enceladus, which is the moon of Saturn. And I tried to put these different bodies here to scale to emphasize that Europa is much lighter than Enceladus, but it also is different in the interior structure. So Europa does have a metallic core, indicating that it is differentiated. The core is overlain by a rocky layer, and that is in contact with an ocean, probably as thick as, or probably roughly 100 kilometers deep. And then Europa has a ice shell, and the thickness of the ice shell is still highly debated. It's most likely between 3 to 4 kilometers. Enceladus has a rocky core, so that means he is not completely differentiated, and the rocky material is overlain by an ocean of about 10 to 30 kilometers, and then an ice shell of 30 to 40 kilometers. And why we are so excited about ocean worlds is because we still want the answer if there is life in the solar system except for us, right? So Europa and Enceladus provide very good parameters that we need for life. So we do have the water silicate interface, which enables the nutrients to be available in the liquid water, which is another parameter we need, the global ocean, or liquid water, but a global ocean is even better. And then we have a high thermal gradient because of tidal heating. So the next slides, I'm mostly going to focus on Europa. So the cool thing about terrestrial volcanism is that if you melt rock, the rock wants to rise because it's less dense. The molten rock wants to rise because it's less dense. That is not the case for water. And that's a problem for cryovolcanic activities because ice is less dense than water. So water is very happy in the global ocean where it's stable and it does not want to rise. So the question is, how do we overcome the negative buoyancy of water? So we do see some indicators that we have cryovolcanic eruptions on Europa. So there is a way to overcome, or there might be a way to overcome the negative buoyancy. So on the left-hand side, we can see results by Ruth et al. 2014. They provided Hubble Space Telescope observations, and they detected hydrogen and oxygen emission on December 2012. And just above the southern hemisphere of Europa, suggesting that there are two H2O plumes with a height of roughly 200 kilometers. Another result by Gilla et al. 2018 suggested that there were plumes based on the magnetometer instrument on board of the Galileo spacecraft. So just to remind ourselves, the Galileo spacecraft is not active anymore, unfortunately. It ended in 2003. It launched 1989 and started operation 6 years after. So the mission is kind of old, but we are still investigating the data and analyzing the data. And these are the best data we have currently for Europa. So that's what we are working with. So this is also, these are also images from the Galileo spacecraft. And I do want to give you some examples of compelling geologic features that could indicate cryovolcanic activities. And we can see here lava domes. The images have a resolution of 200 meters per pixel. And the important thing here is that the lava domes are higher standing than the surrounding, and that could indicate some kind of warmer ice that is upwelling, but we will talk a lot about that in a little bit. Another geologic feature that could be explained by cryovolcanism are these low viscous flooding examples. For example, here where you have very smooth material that is infilling a topographic depression. And yeah, so I do want to present a few mechanisms how we can overcome the negative buoyancy. So first of all, if we put volatiles into the liquid, that could cause explosive venting, and this is shown here in panel A. Another explanation could be that a shallow crustal reservoir gets pressurized, and this pressure can be caused by crustal stresses, for example, due to tidal stresses. But also if the liquid is going to freeze, because then we have a volume change and overpressurize the liquid, could cause eruption. Tidal pumping could also bring material towards the surface. And then warm ice that is rising up, like diapir, could also, for example, form the domes that we just saw. But so these schematics are simple, but they summarize a very unique question we still have. So the question we have is, where would the cryovolcanic eruption would be sourced from? Is it directly sourced from the ocean, or could it be sourced from a reservoir within the crust? And Manga and Wang 2007 investigated the case that a crag is rising and transporting material from the ocean towards the surface. And the mechanism they investigated is that the ice shell is going to thicken because it's cold. And this, due to the freezing of the ocean, that was cause an overpressurization and could bring material up to the surface. However, the results show that the exceed pressure is not sufficient to erupt water onto the surface on Europa. In cases where the icy satellites are smaller, for example, Enceladus and Simios-sized satellites, that mechanism is sufficient. So the excess pressure is sufficient to bring material towards the surface. Another very prominent surface feature on Europa is the chaos terrain. So here we see an image of the Conamara chaos, and it is very characteristic because it looks like that the surface, the crust, actually broke apart and then were rotated but also tilted. So there was a kind of modification of the original surface, and that is very exciting. Brittany Schmidt et al. In 2011 suggested a mechanism where you have a rising thermal plume, and close to the surface you would have a very salty ice layer, and below there a less salty ice layer. And when the plume is rising and reaching the eutectic surface, the ice is going to melt, and you would form meltlands. This change in volume from ice to water would also deflect the surface and cause the crust to break, to fracture and break apart into blocks. Now, if the whole system is going to freeze again, we have a volume increase and there's an upwelling or a higher standing topography, and that is what we see in Conamara chaos. So Now we have seen that brine can be transported to the upper ice shell. Now is the question, can brine, so salty liquid, also move or migrate through the ice shell? And for this, I have a very simplified system here. So we will just walk through that. So imagine you have the following system. You have a block of ice, a block of water, and a block of ice. Now you apply a freezing front on the most left side. What is going to happen is that the ice is going, the water is going to freeze, and at the end you will have the whole entire system frozen. Now, if we add salt to the system, so to the ice as well as to the water, and then apply a freezing front again from the left, we have a brine that freezes. So we are going to have an ice block that is almost pure ice. So all the salt, or most of the salt, is now in the brine. And the brine is also saltier than the adjacent ice salt block. And that causes the salt to diffuse into the ice salt block, because nature likes balances, so they like to balance the salt. Now, we know from cooking, for example, that salt decreases the melting temperature, and thus the ice and salt block starts melting. So the brine block increases here, and at the end we have an ice and salt block, and block that is almost purely ice, and then a brine block on the right. So this process was studied and has been reproduced in various lab experiments on Earth, and we call it brine pocket migration. And yeah, it's known on Earth for a long time, but it's a slow process. So it's, since the Earth is so dynamic, especially ice shield, it's not as impactful. However, on Europa and icy satellites, they have a lot of time. So it could theoretically affect the ice shell. So the question is, can we actually see any evidence on Europa's surface? And the cool thing is, yes, we can. So here on the left-hand side, I show you a geologic map of the Manannán crater on Europa. So the crater rim is roughly where the red unit is. It's one of Europa's biggest craters with a diameter of 30 kilometers. And the cool thing is located here in the central part, where I show you an image from the Galileo mission. The central part has a spider feature, so a radial fractuated system, and that is surrounded by concentric folds. And this is super cool because we know that from Mars, on the left-hand side, you can see a high-res image from a spider feature. And on Mars, these features are interpreted to represent geysers that result from a formation process involving periodic solar insolation, that penetrates through a transparent seasonal CO2 ice layer and heating of the underneath layer. And then you're having a geyser of the gas. And after the geyser formation, after the geyser, you actually form this spider feature. So although there is no CO2 layer on Europa, it is still evidence for a rigid surface that was subject to pressure from below. So our suggested mechanism how we can get that is we had the impact that caused the Manannán impact crater, but with the impact we also had a lot of thermal energy, and those we developed these little brine pockets, and via brine pocket migration, it was able, even though we're in a super cold environment, we migrate the brine pockets and concentrate them in the center. Now, if they were stuck there, they started freezing, and due to the pressure volume change, we get overpressurization and actually form a cryovolcanic eruption. And this is now seen by the spider feature due to the cryovolcanic eruption from the pressure from below, and then also the concentric fractures that are indicative for the volume loss of the partially emptying the brine lands from below. Now, another cool thing about Galileo is that we actually had digital elevation models, so we were able to calculate the volume of the reservoir, or partially emptied reservoir. And in combination with the migration speed, we were able to calculate the concentration in the melt pocket, which was about 1 grams per kilogram. And with that, we were also able to recalculate the initial concentration of salt in the ice shell. And we got about 14 to 60 milligrams per kilograms, and that is a very low value for salt content in Europa's ice shell. It means it's almost clean ice. And now, if we assume that the ice shell was formed due to freezing of the ocean, and we can calculate with the partition coefficient even the salinity of the ocean, and we got 5 to 5.8 grams per kilograms, and that is pretty cool because that lies in the range where modern macroscopic life tolerates salt. So at least with the results we got, the ocean is not too salty for macroscopic life. Now, since we know Europa has a very young geologic surface, it's not getting impacted so much that all the cryovolcanic eruptions on Europa can be explained by that mechanism. However, brine pocket migration does provide a mechanism to migrate brines, and it can be applied everywhere where we have a thermic gradient, for example, also if we have diapirs rising up. So some takeaway points. As I don't want to say as always in science, but most of the cases, the origin of the cryovolcanic activity is still not well understood. We need more missions with Europa Clipper that is going to get sent by NASA, and then JUICE that is going to go to Ganymede, which is an ESA mission. Hopefully we get more answers. There are 2 possible sources where cryovolcanic eruptions can be sourced from. The one is from the ocean itself, and then also from shallow subsurface reservoirs within the ice crust, which is the model that we favored for brine pocket migration. Subsurface melts might be abundant and mobile, and understanding the origin and evolution of cryovolcanic activities can teach us about the structure, but also the composition, for example, the salt content in the ice shell, but also the ocean and the dynamics of the ice shell as well. So for this, I want to thank you for listening to me, and I'm happy to take more questions.
Okay. We have a question from David that says, oh, wait a minute, it's moving on my screen here. Do you think biosignatures may be present in cryovolcanic plumes?
I really hope so. I really hope so. I think it's also important to understand where the plumes are coming from. So if the plumes are directly feeding from the ocean, I think we have a higher chance of detecting any possible life traces. The ice shell itself, I think, is very unlikely to host any kind of biosignature. So if the plumes are coming from the ice shell itself, it might not be very realistic to search. Yeah, we should still search for it.
Thank you. And I'm sorry, that was Don's question, but now we have David's question, which is, are spider features seen with the Earth geysers?
Oh, and that's a good question. I think the mechanism is very different because on Earth it's mostly geothermal activity. For example, if we compare that to the Mars spider features, they are different formation mechanism proposed, but these are actually due to the gas release. So on Earth, I don't think we can see spider features associated with the geysers sourced by geothermal activities.
I think this is Terry has a question that, and it has two parts. The first part is, at Jupiter's distance, do we know how much sunlight can get through the ice crust?
I think at least compared to Mars, it's very dark there. I'm honestly, that's not my home because there was just a side project. So I cannot say how dark or how bright it would actually be.
Okay, and you may then or may not know the second question. Does the amount of sunlight reaching the ocean help with modeling of cryovolcanic processes?
Yeah, I mean, the ice shell is very, very thick. So I don't think that the ocean reaches sunlight at all. I mean, we are far away from the sun, and then we also have this thick. So I would assume that the ocean is very, very dark.
Richard has a question. Would volcanism on Titan, Triton, or Pluto have to overcome negative bouncy since it is based on other substances than water, or would it be more like Earth and Mars?
That's a good question. I would have to see the phase diagram for methane, which, if I remember correctly, is the main material on Titan. So yeah, so I'm not quite sure.
Thanks. From Jacobo, does Jupiter gravity have any influence on Europa's cryovolcanic activity? Perhaps its origins?
Yeah, yeah, it does. So Jupiter is super large and it's having a lot of tidal forces that is pulling on Europa all the time. So first of all, the idea is that most of Europa's heat is coming from tidal forces, and then also the tidal stresses might have an effect on the ice shell. And since the material, so the water, needs to go somehow through the ice shell, it's good if you have stresses because fractures is a good way to bring up water. Does that answer the question?
Okobo, did that address your question? He says, yes, thank you.
Okay.
And we have some other thank yous for you too.
Thank you.
So, and right now, that's all the questions I have. If anyone else has a question, this is the time to ask it. Okay, well, thank you very much, Joanna. You've been really delightful and given us lots to think about. I hope that you will stay through the rest of the meeting and join us for our second, in watching our second presentation, if you can do that in your schedule. But thank you so much, and we hope you come back again sometime.
Thank you for having me and giving me the time to speak.
Sure. I want to make a correction here to our Facebook people. We've decided Facebook to not banish you to darkness.
Okay, I will, David, you're gonna do this, right?
I'm happy to do this. Good evening, everybody. Again, my name is David Rossiter. I'm chair of the NVRC, the Nomination Volunteer Resource Committee. Among other things, we run the annual leadership vote. Last year, of course, the club ran into issues with COVID just like everyone else. And while we were able to move the club meetings online, we had to face how we were going to do the annual leadership election. The bylaws didn't address this situation in regards to voting. Fortunately, the board. I don't know why she's calling me, but here we go. Somebody call May, okay? She tried to call me, and maybe Jim, you could call her and see what you can work out here.
I will.
Thanks. The club's bylaws didn't address the situation of not being able to vote. They basically said we vote at meetings. Fortunately, the board was able to find a way to authorize voting at the online meetings using Zoom and using the same registration and membership verification procedures that we're using tonight. These procedures are really work intensive, really clumsy, challenging for the vote administrators. So since then, the NVRC has proposed changes in the bylaws that specifically allow online voting, and while maintaining the ability to vote in person when that becomes possible again. There's a few other related changes in order to make our voting just as flexible as possible. So we, the NVRC, worked with the board, specifically Doug Smith, and thanks, Doug, for all the great work you've done to make this happen. And he put the changes into words, if you will, that fit into the bylaws. And they were approved by the board of directors. However, we have to approve it by the membership. So to do that, first off, we have to review the changes at a meeting prior to the vote, which we did in December. So the changes were reviewed in December. We were open for questions. And in addition, we've made available a document that outlines the changes and made that available to the membership over the last month. And I put a link into the 2 emails I've sent out for registration for this meeting as well. So it's all been made available to you, and hopefully you all understand it and support it. So we've put it all open. We've been open for questions, and tonight it's just about putting the vote together. So we are going to vote now whether to accept or not the proposed changes in the bylaws. Specifically, the wording you're going to be voting on tonight is, and I hope I have this right, Terry, I approve of the Constitution of Bylaws changes presented at the December 2020 membership meeting. And you can answer yes, no, or abstain. In just a moment, Terry's going to post the vote question on Zoom here. You'll see a window pop up. Just click on the answer you want. Yes, no, or abstain. Yes, there is an abstain in case you want to make a political statement there. But the important thing is after you click on how you want to vote, whether you vote yes to approve them or no not to approve them, after that, be sure to hit the submit button. We don't see it till you hit the submit button. That's it. Once everybody's voted, Terry will display the results. We need 2/3 approval in order to make this work. If you have any problems, post a note in the chat. We'll try to help. If you still got a problem we haven't noticed, go ahead and unmute and quickly ask or find out. Let us know what the issue is and we'll try to help. But prefer to do that over chat if at all possible. Did I cover everything, Terry?
Do we need an official second to this kind of a vote, or?
I don't think so. Not that I know of at all.
Hey, Dave,
Yeah.
might mention that the voting is only for the registered members, not for the people who are watching on Facebook and people who are not registered members.
That's a good point. For those of you on Facebook, we required registration for this meeting, and then I went through all the people who registered and verified that they are members of the club, and that's why only members are on the Zoom portion of this meeting tonight. So those of you on Facebook, you just get to watch the fun. I don't think you'll see a pop-up window. You may, but you won't be able to click on it. Only people on Zoom will be able to click on it. Thanks, Doug.
Okay, so we're going to open the poll, right?
Yes,
And
please.
I will give you guys a warning before I close it, okay?
Thank you, Terry.
Got it.
So it's up there. Just click what you want and be sure to hit that submit button when you're done.
Voila.
It's your one chance to abstain from something, Doug.
Thanks, Ralph, but I wrote them, so I'm going to approve them.
I know, I'm just messing with you, bud.
Somebody asked about a family membership. We did try to outline in both our emails out there that if you have a family membership and you both want to vote, you both had to register separately for the meeting and come online separately in order for both of you to vote. So that's how we had to arrange that.
Okay, the vote's been open for a minute, and we have 90% of the people have voted. I'll leave it open for another 20 seconds. And I'm closing the polling unless I hear otherwise. And I will share the results.
Okay.
Wonderful. Thank you, everybody. I appreciate 100% accept the changes. For those of you on Facebook, this is a real live member-driven organization. And yes, we all have a say into how the organizations run. And as the chair of the NVRC, we're always looking for people to volunteer and get involved so that everybody has the opportunity to get involved. And we'd love to have you come and join us if you're not a member right now.
Somebody could have voted
everybody.
against this.
Passed. I'm
Because
sorry?
this looks like an Eastern Bloc election. So we should have had one or two votes symbolically against it, just so it would like we're an Eastern Bloc country.
Well, usually Doug takes care of that for us.
Just kidding, just kidding.
That's great, everybody. Thank you. Hi, May, you're back.
Yes, I'm back. I don't know why I went away, but I'm back. So
Welcome back, May.
thank you. And thanks to Terry and David and Jim Knoll for taking care of this when I got lost there for a bit. So, well, David, is there anything else that we need to do in terms of elections at this point?
Not at this point. When we get close to the spring election, we will send out and brief everybody during meetings and send out explanations as to how the voting is going to go. It's going to be completely different than how we do it tonight and should be much, much more convenient and even allow you to vote in advance as if you were an absentee voter. So it's going to be super flexible and I think you're going to enjoy the experience. So thank you, everybody.
And thank you and your committee for being so helpful with us and developing some mechanisms to update us in terms of easy voting and with technology.
Thanks for that, May, and they're all on here tonight, so I know they heard you. Appreciate it.
Good. Yes. Well, we appreciate you did a lot of work, and we are grateful for that.
And thank you, Doug.
And so I hope now that our Facebook people will be able to be more entertained at this point, and get more astronomy information. Our second speaker tonight is Dr. Mary Turner, who is our master observer for the club, which involves meeting a lot of requirements in order to qualify as a master observer. And Mary quarterly does a talk for us on seasonal objects in the sky. And so, Mary, are you ready to screen share?
Okay, let me.
Got it.
Is there?
Yep.
Great. Yes.
Oh,
Mary,
oh,
are you going to turn your video on?
it's on. I suppose. Let's see if I can find the little thing because I moved. Okay, so. Okay. Well, it says it's on.
Yes, we've got you now,
Oh,
Mary.
okay. Okay, well, I won't be looking because I got my presentation on another monitor, but that's life. Okay, so welcome everyone to the, as May mentioned, my quarterly presentation. And I know that I have to be done by 20 after 8, or Terry will tell me to stop. Right, Terry?
That's the plan, yep.
Okay, so we'll go through. I'm not going to rush just to get done on time, but we'll see how far we get. Should be close to done by then. Okay, come on, mouse work. Okay, here we go. So this time of year, there are some really beautiful constellations, but I can't talk about Orion all the time. Well, yes, I can, but I won't. So I'm not sure what that message means. So this time around, we'll talk a little bit about Auriga, some interesting lore on all of the ancient constellations. So we'll talk a little bit about Auriga, and I did find a way to work Zeus into it, sort of off. Not as direct as usual, but Zeus at least gets mentioned, and then a couple of other objects within Auriga, as well as variable stars, supernova remnants, lots of open clusters. I like open clusters, and a Struve star system, just because it's an interesting distribution of stars. But let's start looking at the different objects. Again, Auriga is the charioteer, and there are several. We obviously go online, go into the sky. You can get lots of the little graphical, pictorial images of what the charioteer looks like. This is from the sky. This is a Middle Ages type reference. But the interesting thing about Auriga, the charioteer, is he always goats, but never a chariot. You would figure if he was a charioteer, he'd have a chariot, or there would be a constellation nearby or a grouping of stars nearby that might represent the chariot. No, we've got a charioteer, but no chariot. And fortunately, some of the myths, the lore that we have does sort of explain that as well. But always there are goats, and the goats are, when we've talked about a lot of constellations, or when I talk about the constellations, I talk about some of the history and how for a large number of constellations, the basis was developed by the Sumerians, the Babylonians, in that region. And then as other areas like Greece and Rome conquer those areas, they sort of usurped some of their myths and legends. In this particular case, there is only a slight overlap in that for the Sumerians, it wasn't a charioteer, but it was the goats. So the goat part of the constellation does go back to the Sumerians, but the charioteer aspect is more related to the Greeks. It's something they came up with almost on their own. But again, a little bit of the lore and about this particular constellation. It's always fun to think about a little of the history, if you will. It does, in the primary legend we'll talk about, relates to Erichthonius. I got that right. I keep wanting to put the I before the O, who was a king of Athens. He was the son of Hephaestus, which made him the grandson of Zeus. See, we got to get Zeus in here someplace. He was raised by Athena. He is credited with being the first human to figure out how to hitch 4 horses to a chariot. A lot of the lore indicates that he was lame and therefore had difficulty, riding a horse, or could not stand on a chariot with 2 horses, needed the seating type chariot that you could have with the 4 horses. He in particular used his chariot in a battle against a particular king of Thermopylae, Amphictyon. Amphictyon sort of stole the crown. Nobody really recognized him as the legitimate king. So when Erichthonius overthrew Amphictyon, it was liked by everyone because they didn't like the other guy who came into power by getting rid of the legitimate king. Because he was raised by Athena, she continued to protect him, and therefore he was able to reign as king of Athens because he had the protection of Athena. In honor of Athena, he began the Pan-Athenic Games, which were held in Greece every 4 years. They are real, starting in 566 BC, and they continued on for almost 700 years. They're very similar in some ways to the Olympics of today, except it wasn't all about strength and athleticism. It was also about religion and culture. So, a little bit more classy Olympics, if you will. And again, I guess I copied that line twice. Again, figured out how to hitch horses to a chariot. He also showed the people of Athens how to use chariots and horses to plow and to till their fields. Okay, so he had difficulty walking, and no, I haven't mentioned yet that part of the reason he was only, had difficulty walking was he was half man, half snake, which wasn't quite shown in some of the pictographs we looked at earlier. His father was Hephaestus, have to look at it to be able to pronounce it correctly. His mother was the earth, hence the part snake. The chariot did allow him to move around quite a bit. And during these pantheonic games, he actually competed as a chariot driver. So we do sort of have a chariot associated with this legend, but again, not in the sky itself amongst the stars. But basically, Zeus, his grandfather, found that his skills with the chariot, inventing the chariot, as well as his skills in battle, were sufficient to earn him a place in the heavens. Hence, he assumed his rightful place within the sky. And again, that we talk about Auriga the charioteer, no horses, no chariot, but you do have the reins and the whip in one hand. The other, you have a goat, and then you have another star grouping that are the 2 kids, the 2 young goats. And as I mentioned, the goats actually are the only part of this star grouping and the mythology associated with it that we can trace all the way back to the Sumerians, where Capella and a few other stars that make up the charioteer were actually considered to be the staff of a shepherd. Now, of course, you can never just get by with one myth and legend. You've always got to have a couple more. And this one is interesting because it sort of addresses in its own way why the charioteer doesn't have a chariot. In this particular case, we'll say that Auriga represents Myrtilus, who was the son of Hermes, another one of the Greek gods, who served as a charioteer for King Onomus. The king had a daughter, no sons. So since daughters couldn't become, couldn't rule the territory, needed to find a proper husband for the daughter to take over when the king passed on. So the king set up a chariot race, and the winner of this chariot race would be allowed to marry his daughter, Hippodamia. Where do they come up with these names? Now, during this race, and Myrtilus did participate, his chariot was destroyed. However, there were a couple of not so nice competitors in the race, and he helped take them out at the same time, which allowed Pelops to win the race and win the hand of Hippodamia. And in thanks for helping him win the hand of Hippodamia, Pelops killed him. What that gratitude? But then again, it's a Greek. It's a myth. Nobody lives in these things. And in this particular case, since his father was the god Hermes, he was placed in the sky by Hermes. And I love Hermes. Hermes was the herald, and he's the protector of heralds and of travelers and merchants and orators and thieves. I'm not quite sure I understand the connection of how the thieves got in there. I was going to make a comment, I won't. The charioteer, the constellation itself was sort of recognized by the pentagonal shape of the stars, but unfortunately one of the stars that made up that shape is out now, actually sort of been booted out of Auriga and is now part of the Taurus constellation. So what is now called Beta Tauri used to be Gamma Aurigae. It does point away from the galactic center, so there's a lot less of the interstellar gas and dust that allows us to look sort of, for lack of better terms, through this constellation relatively easily, in particular with telescopes. So this is why we get to see lots of open clusters. This was, as I said, goes back to the Sumerians. The actual constellation of Auriga, the charioteer, was more developed by the Greeks, and it was one of the original constellations of Ptolemy. So that's a little bit of relatively nonviolent lore. I don't do that often, but every once in a while we need to get away from the violence. So the next object is going to be one of the bright stars in our sky, Alpha Auriga, or Capella. And here's our little star maps, and I'm getting pretty good at remembering to put the RA in deck, as has been requested several times. And again, we can see down here that this Beta Tauri right here used to be Gamma Auriga, which is what made the full shape of the constellation. So the star is still there, it's just been given a different home. And nice picture here showing that Capella is, of course, as are a large percentage of stars, actually more of a star system. Capella, going back to the Sumerian lore, the name Capella basically means female goat. Capella sounds much prettier. It's the 11th brightest star in the sky, but it's the 3rd brightest that we can see, following only Arcturus and Vega. And obviously, since it's very bright, it simply means, among other things, that it's relatively nearby, so about 42, close to 43 light years away. It's actually made up of 4 stars, 2 separate binary star systems. We can easily see the pair of yellow giants, just seen in the previous picture, but there's also a pair of red dwarfs. The surface temperature of the yellow giants are 4,900 Kelvin and 5,700 Kelvin. Remember, our sun is about 5,600 Kelvin is the number I always used in grad school. Sizes of the two are 12 and 9 solar radii, respectively, and about 2.7 and 2.6 times the mass of our sun, but significantly more luminous. Again, they are giants at 79 and 78 times that of the sun. So they are very equivalent, if you will, stars. The second pair, don't try to look for. They've been confirmed spectroscopically. They're about 10,000 astronomical units away from the giant stars. Remember, an astronomical unit is the sun, the mean sun-Earth distance. So they're a very, very far distance away, but they are gravitationally bound, and they have about a 400-year period. But again, lots of interesting science can be done non-visually, and spectroscopy is a lot of fun. Some of my first jobs were designing spectroscopic instruments for large telescopes. Okay, so now we're going to start looking at a couple of other interesting objects. And again, as you can sort of see as we look here, there are lots of clusters that we can see simply because we're looking away from the dust, so they're much more visible. And here's a nice picture from Canada, France, Hawaii telescope. I designed an instrument for them a long time ago. That was previous existence. Okay, a little bit of information if you want to talk about this at a star party when we get to have one of those again. There are about 2,000 stars within the system. Only about 150 of those can be easily seen, but it is a relatively populated system for an open. It's about 4,500 light years away. Remember, open clusters are nearby, globular clusters are far away. About 25 light years in diameter, which works out to be about 25 arc minutes. And remember, we think about our sun being about 30 arc minutes. So the size of the concentration of stars is on the scale of the moon. So if the moon would fill your telescope, so would this cluster. Scaling properly. It's relatively young, 350 to 550 million years old. There are a large number of red giants, but there are also a very significant number of white dwarfs. The metallicity, so if we think about the formation of the universe starting with hydrogen and moving to helium, as stars form later, they have more material that's other than hydrogen and helium because they're made up of the results of supernovas, novas, etc. So having a metallicity slightly higher than the sun indicates that, yes, on average, these stars are going to be younger than our sun. They were formed later from more complex material. Total brightness is about 6.2, so in your telescope you will definitely be able to see it. The stars are, on average, not that different from our sun, so we've got about 2,000 stars with a total mass of about 2,500 times that of our sun. So we don't have a lot of massive stars here, in other words. But again, it's a very nice, pretty object to look at. One of those eyepiece full of stars type objects. So now we'll talk about variable stars. Those are always fun to look at as well. This is Heinz Crimson Star. So we see it indicated with this little red circle here. And again, the coordinates. And here is sort of a picture that I took, and it's referred to, among other things, as the vampire star because it is very, very red, largely because of the carbon content. Carbon is an absorbing material for some wavelengths, so it is going to appear a very bright red, much more red than we would be thinking about when we think about stars. But it is, if you take a look at it in your telescope, it is very red, an interesting type of red. Heinz's original description was, it was like a drop of blood on a black field. Nice way to think about it. I mean, it's definitely a visual way to think about it. It is a variable star. The magnitude goes from about 6.9 to about 8.6 over 444 days. So it's a Myra-long period type variable. As a carbon star, it's in a very late stage of its life cycle. It is currently fusing carbon. It's going to look reddest when it is dimmer. It's about 1,300 light years away. Right now, it's about 400 times the size of our sun, but only about 2.5 times the mass of the sun. Temperature is quite low, about 2,200 degrees Kelvin. It does have a very high luminosity, 6,000 times that of the sun. However, most of that is going to be in the infrared. You're not going to be able to see that. You'll see this 7 to 8.5 magnitude red star, but there is a lot of energy coming from it in the infrared wavelength region. My old home. Okay. I tried every time not to talk about some of the really cool things, but there are just several objects that I need to rotate through just because I want to make sure everybody remembers to take a look at them, and more importantly, lets other people, again, when we can go back to having star parties, look at them as well. So the M1 Crab Nebula, it is an interesting object to look at. But I also like the history of it in that, we can actually trace back the history of this object. And yes, with your telescope, you're not going to see as well as you could with WIFPIC on the Hubble or at the Palomar, but you will be able to see reasonable detail in your telescope. You'll certainly be able to show or see it yourself and show it to other people. So this was with a 12.5-inch Newtonian telescope. So it's fairly large. Okay. It is, as I said, it has an interesting history behind it. It is a supernova remnant, but it is a supernova that we can trace back to when it happened or when it was first seen. Obviously, it's light years away, so we saw it 6,300 years after it actually happened. However, in 1054 AD, it was known to have been observed by Chinese, Arabic, and Japanese astronomers. Some of the information from that time indicates that it was about 4 times brighter than Venus. It was visible in daylight for 23 days. And visible in the night sky for 653 days. So for almost 2 years, you could see it in the night sky. Just said that it was 6,300 light years away. Right now, it's somewhat dim, about an 8.4. It's definitely a telescopic object. It is very small, 6 arc seconds by 4. It's about 10 light years across and expanding at 1,800 kilometers per second. Again, supernova blows up and keeps spreading out until something stops it. The pulsar in the center is a neutron star, about 12 miles across. Mass is greater than that of the sun, and it's revolving around at about 30 times a second. And just a few other pictures, some of them showing the changes over time as as we look at this object, particular in the shock waves that are coming out. So another really pretty cluster to look at is M44, the Beehive cluster. This is located within Cancer. And again, it's beautiful to look at. It's not as occupied, if you will, as some of the other clusters, but it is a nice grouping of very bright stars, somewhat visible to the naked eye under good conditions. Obviously, it looks much better in a telescope, but if you're not quite sure where, if you're looking at it, yeah, you can look up in the sky and actually see it. Even I can see it, and we know how good my eyesight is. It's relatively close by again. It's an open cluster. This one only about 600 light years away. Visual brightness is 3.7. As I said, you can see the haze in the sky. Angular dimension is 95 arc minutes, so about 1.5 degrees, and basically about 3 times the size of the moon. It will see it as a nebular or cloudy region, again, visibly as well as through your scope. Galileo saw about 40 small stars. Better instruments can show about 1,000 members, several red giants, and several white dwarfs as well. Again, it's an open cluster, so it's relatively young. This one's a little bit older than the last one, but it's only about 750 million years old. Same age and relative motion as the Hyades cluster, which means there's a significant likelihood it was probably formed from the same gas cloud that formed the Hyades. Okay, so the Christmas tree cluster, as well as the other objects located around it, the fox fir and other nebulas, over in Monoceros. And we're right up here. So if you can find Betelgeuse, although it's in Monoceros, it's, look at it between Procyon and Betelgeuse, and you're going to be in the right area to be looking. And here is a nice picture showing the whole region of the sky, the Christmas tree itself. I have another picture. There are too many stars here to really see the triangular shape of the Christmas tree. But and sometimes you look at these things and look at the names and you say, where did they come from? And this is the Cone Nebula, and I can see that as a cone. And I don't know how well this picture comes across for you. This is the Fox Fir Nebula, and I got to admit, I see the fox right there. We see the snout of the fox, the nose, the mouth, the eye, and then of course the pelt, because we don't see any legs. But that one really does look like a fox fir. And so here is looking at the Christmas tree cluster coming out from the Cone Nebula, and you can see the triangular distribution of stars that really does sort of look like a Christmas tree. And this is S. monocerati down here, also obviously part of the Monoceros area, but definitely I'm willing to buy off on that as looking like a Christmas tree. I'll buy that off that being a cone, but I think the fox fir is probably one of the nebulas that's most appropriately named. There's no, squinting your eyes to see the fox. It's definitely there. Little bit of information, again, in addition to the open cluster, there are also the Cone and Fox Fir nebulas are two of the named nebulas within that large region of nebulosity. It's about 2,500 light years away, and it is extremely young, about 100,000 year type young, only about 40 stars, but much more than that, we wouldn't be able to see it as a Christmas tree. Angular diameter is about 30 arc minutes. So again, about the same as the moon. Magnitude is 4, but spread over a relatively large area. The star at the base has a magnitude of about 4.6. The star at the top by the Cone Nebula has a magnitude of about 6. Although there are 40 stars in the region that we're going to call the Christmas tree, within the whole nebulosity itself, there are probably approximately 600 total members. Hard to really see because, as you could see from looking at this nebulosity, it is quite dark in some areas due to the dust. So there are probably more stars than we necessarily can see. So the next Messier objects to talk about is Messier 46 or NGC 2437, as well as a separate object that is effectively co-located, NGC 2438. And 2438 is right here. Isn't it cute? A nice little planetary nebula that appears to be within this open cluster of stars. And again, a really, really nice eyepiece full of bright, very intense, bright, whitish blue stars with a little planetary nebula sitting there as well. Obviously, we're looking at primarily at an open cluster, but again, also at the planetary nebula. It's about 5,600 light years away and only about 300 million years old. So again, relatively young stars. Visual brightness, about 6. Again, something that if you know where you're looking, you're going to be able to notice this concentration of stars in the sky. Parent dimension is about 27 arc minutes. Again, relatively close to 30 arc minutes. So relatively close to the extent of the moon, which at this distance works out to be about 30 light years across. There are more than 500 stars in total, plus the little planetary nebula. Planetary nebula only appears to be within the cluster. It's actually much closer to us, only about 3,000 light years away, and obviously much, much dimmer, only about a 10.8 magnitude, and much, much smaller as well, obviously, because planetary nebulas do tend to be a whole lot smaller. But again, it's an interesting juxtaposition that just, by circumstance just happens to be there. But those are always the interesting things to look at and to show people. Okay, so now let's talk a little bit about Messier object number 50, also in Monoceros, and also an open cluster. And we can see right here, I like clusters. It's about 3,200 light years away, so about the same distance as that planetary we just looked at. Brightness is 5.9. Again, you'll be able to see what you're looking at. Diameter is about half the size of the moon, 16 arc minutes, which corresponds to an actual diameter of about 20 light years. About 200 stars within the grouping, only 78 million years old. On the age of the universe, that is a definite only. To us, it might sound older, but 78 million, these are very, very young stars. The red stars that we're looking at are not obviously part of this very young cluster. These are just happen to be in that direction in space. They're closer to us than the actual cluster stars. Okay, so the last object, and yeah, I still got a couple minutes, so we're okay on time, is Oscar Struve's object 147, and it's located right over here. So again, it's in the area of Auriga, just right over here. It's not specifically indicated, but I got a picture right over here. So we can see that the sigma 3, psi 3 is here. And this is the Struve 147. And the neat thing about this object is it is a grouping of 3 stars, and it's virtually it's a really nice triangle. So it's just an interesting grouping of stars. This is that's a separate Struve object right there. This is a combined, a system of 3 stars, so they are gravitationally bound to each other. And again, sort of just an interesting object to look at. It's very pretty. The primary star is yellow, orange type color. The 2 companion stars are blue. Magnitudes are, total magnitude is about 6.6. The primary being about a 6.8, and the 2 blue companions are much dimmer, 8.7 and 9.9. And I believe that is it for this quarter. So thank you all very much. And I will talk to you again in 3 months. Okay, and there you go, May. You can have the screen back.
Let's see if we have any questions. There was a question in the chat at one point about what about Sirius, and someone else said it's in the southern hemisphere. We have no Facebook questions at this point.
I talked about Sirius last time, so I couldn't talk about it this time.
Okay. Okay. Do we have any other questions for Mary? Okay, there's no Facebook questions either. So thank you very much, Mary. We always appreciate your presentations with us and sharing some different perspectives. And so thank you very much.
They're no fun when I have to sit down.
Oh, yes. And you like to move when you talk, yes. So it is more difficult that way when you have microphones to deal with.
Mm-hmm.
So, okay, for the next part of the meeting, we're not doing our breakout rooms tonight simply because we had the 3 activities and we wanted to kind of focus on those and make sure that we had enough time, for all of those as well before people got really tired. But we now can open it up for discussions and comments and any questions people want to raise about TAAA matters or anything like that. So do we have comments from people?
Before we do that, do you want to say goodbye to the Facebook people?
Oh, yes, our Facebook people are leaving us. Okay. Thank you so much for coming and joining us tonight. And we hope that you will continue to come. We usually meet the first Friday of the month, but since that was New Year's in January, we changed it. But we'll be here the first Friday night of each month. And we would love for you to join us, and again for you to also look at our website at TucsonAstronomy.org. So we'll look forward to seeing you again.